Relations of wind turbine and Bernoulli's principle. Table of contents. First, the evolution of wind turbine, how wind turbine works, and the relationship between the aerofoil blade and Bernoulli's principle, the design of the blade, and also what is the types of wind turbine.
Evolution of wind turbine. Wind turbines have a long history, starting with ancient civilizations using basic vertical axis windmills. Horizontal axis windmills emerged in Europe during the Middle Ages and were used for grinding grain. The Industrial Revolution brought advancement, and the first electricity generating wind turbine was built in 1887. A Scottish electrical engineer, Professor James Blyth, built a closed-cell wind turbine in his garden that generated currents to power lights in the cottage, which thus became the first house in the world to be powered by the wind-generated electricity. Modern wind turbines began to take shape in the 20th century, with technological advancement improving efficiency and durability. Wind power expanded rapidly in the 21st century with larger turbines, offshore installations, and improved grid integration. Today, wind turbines are a major source of renewable energy worldwide. How does a wind turbine work? First, the kinetic energy contained in the air current will rotate the turbine blades, and the blades are actually attached with a low-speed shaft located in the nacelle. And in the nacelle, there is a gearbox, functions to accelerate the speed of the low shaft to increase the electricity and transfer the energy to high-speed shaft, which is connected to a generator that converts the kinetic energy into electricity. And this electrical energy will passes through a transformer that steps up the voltage to be transported on national grid or by local site to powerhouses. There are three primary factors that determine just how much energy wind turbine can produce. First is the size and the orientation of the blades. The second is the blade's aerodynamic design, and the third is the amount of wind turning the rotor. Wind turbine can be designed with rotor on the vertical axis or horizontal axis. Vertical blades can pick up wind coming from any direction, but with much less efficiency than horizontal axis rotors. Horizontal designs allow blades to capture the wind's full force by tracking the wind direction and turning to face it, hence making a horizontal axis of wind turbine more popular. How is the design of the blades of a wind turbine that helps to increase its efficiency? The blades have a lot of airfoil cross-sections consisting of different sizes and shapes from the root to tip, and the blade is also twisted. This is due to the fact that curved blades suffer from drag along its length, which tries to stop the motion of the blade. Drag is essentially the friction of air against the blade surface. Drag is perpendicular to leaf and is in the same direction as the airflow along the blade surface. But we can reduce the drag force by bending or twisting the blade and also tapering it along its length, producing the most efficient wind turbine blade design. The angle between the direction of the oncoming wind and the pitch of the blade with respect to the oncoming wind is called the angle of attack. As the angle of attack becomes even larger, more lift is created. But as the angle becomes even larger, greater than above 20 degrees, the blade will begin to decrease lift. So there is an ideal pitch angle of the rotor blade that creates the best rotation, and modern wind turbine rotor blades are actually designed with a twist along their length from a steep pitch at their root to a very shallow pitch at their tip. This ideal angle of pitch is called as the optimum angle. At the root of the blade, where it is attached to the hub, the wind speed is relatively lower compared to the tip. To ensure that the blade maintains an optimal angle of attack and generates enough lift, the twist of the blade increases the angle of attack at the root. This allows the root section to effectively capture the wind energy. As we move towards the tip of the blade, the wind speed increases. To prevent excessive drag and maintain efficient performance, the twist of the blade gradually reduces the angle of attack. This adjustment helps to balance the aerodynamic forces along the length of the blade and ensures that the tip section operates within its optimal range. The magnitude of blade velocity increases linearly as we move from the root to tip. So, angle and magnitude or relative velocity of wind varies along the length of the blade. The apparent velocity becomes more aligned to the core direction as we move to the tip. This causes the differences in the angle of attack at every airfoil cross-sections. Hence, there should be a continuous twist in blade so that at every airfoil cross-section, angle of attack is optimum to reduce drag force and ensures efficiency. Aerodynamic explanation. The wind turbine rotates based on the Bernoulli's principle that focuses on the velocity of fluid. If we look at how fluid flows around the airfoil, we can see that close to the leading edge, there is a point where the fluid velocity is reduced to zero. This is called the stagnation point. Outside the thin boundary layer surrounding the airfoil, the fluid above the stagnation point above the top surface of the airfoil travels faster than the fluid traveling over the bottom surface, as we can see from these particles. Bernoulli's principle tells us that when the velocity of fluid increases, its pressure must be reduced, which is just a statement of the conservation of energy. This means that the increase in velocity above the airfoil creates an area of lower pressure, and the reduction in velocity below it creates an area of higher pressure, and this pressure difference creates the lift force. First, it is due to the geometry of an airfoil that causes the flow to be pinched together above the airflow, but not below it. Because the conservation of the mass, this results in increased velocity above the airfoil. Another explanation for the difference in velocity is based on the concept of circulation. The flow of airflow around an airfoil can be thought of as the superposition of idealized uniform irrotational flow and circulatory flow, or we call it as laminar flow. Without circulation, the flow around the airfoil will look like this. This is clearly non-physical since the fluid can turn a sharp corner at the trailing edge. So the airfoil must be generating a sort of circulation. If we impose a condition that says the flow above and below airfoil must be parallel when leaving the trailing edge, we can calculate the exact amount of circulation that must be generated by airfoil to do this, and is called as Coulthard condition. Circulation has the effect of accelerating the flow above airfoil and delaying the flow below the airfoil, which gives us an explanation for us to apply the Bernoulli's equation. There are other types of wind turbine. First is the vortex bladeless. The bladeless vibrate and move back and forth to harness kinetic energy as it has no blades. Then the tire wind. The blades move just like a wing of birds is flapped and is used mostly offshore. Then the quiet revolution. It can collect wind from all directions. Finally, the alterable. The higher it is from the ground, the higher the wind and the higher the energy is generated to produce electricity. To conclude, the physics concept is used to explain the efficiency of different types of wind turbine design. The design of airfoil cross-sections area of the blades of wind turbine is important to optimize the efficiency. This characteristic enable humans to generate power for electricity users in daily life. That's all from me. Thank you.